Hello and welcome to today's video. We're doing it on continuous functions. So, to actually give you an intuition into what a continuous function actually is, let's take an example which is a very common one. For example, a car is moving in a straight line with the initial velocity u and is uniformly accelerating with an acceleration a. So the time t is represented by t. And hence I could give the final velocity of that car in terms of this equation. To draw the graph of this function, as you can see that it's a straight line with slope a, which is the acceleration of the car. Over here, if I take an example that for any particular time t, I have some variable x which is also representing time, the function of x, and here is the velocity at that particular time t. So if I try to move this value x closer and closer to t, I can see that f of x also tends to move closer to vt. That is, if x tends to t, I can say that f of x tends to vt. Here what I mean by 10 is that it's just moving closer and closer to the value vt and t. So I can say that if I try to move x closer to t, f of x moves closer to vt. It doesn't matter what path that it follows, it has to just move closer to vt. It could be any random path taken. Hence I could actually give an informal definition of continuous functions in this manner. To actually define the conditions for a function to be continuous, I will be using the concept of limits of a function. So I'll try to define the limit of function by first defining what a neighborhood of a function is, and hence I will try to relate the neighborhood of a function to what the limit is, and I would ultimately use the limit to actually bring about conditions for a function to be continuous or not. But before that, let me give you an example of what a non-continuous function is. For example, y is equal to x minus step x. Over here, x minus step x has fractional part of x. Fractional part of x, the graph of that is and it goes on to the negative side as well. So on and so forth. Over here you can see that as I try to bring the value of x, let me take that the value of p is over here, or the value of p is anywhere, it doesn't matter. If I try to bring the value of x closer and closer to this value of 1, this function isn't defined for 1, and hence there's a sudden jump in the value of 0.9999 to 0 again. Hence a condition necessary for the function to be continuous is that there should not be any sudden jumps in the value, as in this case. Now to limits of a function. To actually say what limit of a function is, let me actually define what the neighborhood of a function is. I will be denoting this by the neighborhood of a, it's any real number, and neighborhood of p, it's also any real number. Over here, a, the symbol used f of x tends to a when x tends to p. To actually understand what this means, I will use the concept of the neighborhood of a function, and hence if I have a range of values that is symmetric to p, that is p is the midpoint of that range, I could say that by representing it on the number line, these are the limiting values for that particular range, where R over here is the radius of the neighborhood. So if X belongs to this particular neighborhood, it could be anywhere, X could be anywhere, it doesn't matter. Since the neighborhood of that particular function is an open interval, I would say that X is less than P plus R and is greater than P minus R. So over here, on further solving this, I can say that the modulus of this difference between P and X is less than the radius. It is evident from the real number itself, the real number line itself, that this is obviously less than this, that is the radius. It is a convention to actually represent the difference, that is this difference that I mentioned before, in terms of delta. Similarly, for the neighborhood of a function which tends to A, for this particular value, the neighborhood of this A, I could say that any value f of x would be less than A plus R, greater than A minus R, where R is the radius of the neighborhood for this particular value A. A over here is equal to f of P. That is so. On further solving this as well, I will get the same result. That is this one. The same difference over here is represented by the Greek alphabet epsilon, and hence I could actually call this type of defining limits as the epsilon delta definition of limits. So this defines the neighborhood of the values P and A. When I have such a condition, if I plot the graph, the y is equal to f of x, this is x over here. I have that value P, and I have the neighborhood over here. Similarly, hence if I can say that for any value of A, and if f of x belongs to the neighborhood of A, then there exists an x which belongs to the neighborhood of P. It doesn't matter how small the neighborhood of P is, it has to belong to the neighborhood of P, because f of x belongs to n of A. So I can say that the limiting factor, the limiting region over here is this shaded portion, and hence for all values of f of x above this particular neighborhood, the function is continuous as the limit of the function exists. I am not talking about continuity of a function right now. The limit of the function exists for all values that is just above this neighborhood, and it isn't necessary for the limit to exist at p, for the function to be defined at the point p, for the limit to exist at that point p. So using this tool of limit of a function, I could define the continuity of a function by forming this condition, that is, the left hand limit is equal to the right hand limit, that is of the function, is equal to the function at that particular point p. Now what is left hand limit and right hand limit? The left hand limit is basically when we approach p from the left side of p. I am approaching p from the left side. So I represent the left hand limit as x tends to p negative of f of x. Over here this sign doesn't indicate anything regarding the value of the x, that is the variable x next to p. It just indicates that we are approaching p from the left side. Similarly, the right hand limit will be p positive, that is we are approaching from the right side. Over here, for the limit to exist at this point, y LHL is equal to RHL is that, as I said in the beginning, for a function, if I try to bring about a value x closer to p, the value of f of x should tend to move closer to a. Should move closer and closer to a. It doesn't matter what part it takes in this process. So this should stand true for both the sides. That is, if I try to bring a value of x that is over here closer to p from this side, as well the f of x should tend to move closer to a. And hence, for a limit to exist at that point, I must prove that the left hand limit is equal to the right hand limit. Now, for a limit to exist, I had told before that the function need not be defined at that point p, because we are trying to bring x closer and closer to p, but not exactly make x equal to p. But for a function to be continuous at that point p, not only that LHL should be equal to RHL, but the function should be defined at that point p, and the value of that function at point p should be equal to this limit, because we are trying to prove that as x becomes closer and closer to p, the function's value is approaching. The actually defined value of the function for that point of p is supposed to be equal to the left hand limit or the right hand limit. I had taken an example, f of x is equal to u plus ax. Using the concept of limits, I would prove that this function is equal to 0, that is, the condition LHL is equal to RHL is equal to f of p. Over here, x represents time, so let p, that is time, equal to 3. Now, for the left hand limit, I have limit of x tends to 3, negative on the top, that is because I am approaching the point p from the left hand side. So, function is u plus ax, this is p equal to 3. So x is tending to p from the left hand side. So I can, this difference between x and p is represented by another variable h, that is p minus x is equal to h. So I can say that that x tends to 3, that is p, is equal to x plus h. So this is represented by p minus h, x is represented by p minus h times a, and over here the h value tends to 0, that is, I am trying to bring x closer and closer to p, so the difference h over here will be tending towards 0. Hence, p is 3 minus h tends to 0 times a, so that is equal to u plus 3a. Over here, everything else are constants, hence the only variable being h, the limit is only applicable to h. I have converted the limit x tends to 3 in terms of h tends to 0. Now similarly we will be trying to find the right hand limit as well. The limit of x tends to 3 from the positive, that is from the right hand side, f of x, that is limit x tends to 3 positive u plus ax. Again, from the number line it's evident that when I try to bring x closer and closer to p from the right hand side, this difference is h again, and x is greater than p, so x is equal to p plus h. So over here x will be p plus h. Again, I am trying to bring x closer and closer to p, so the difference tends to become 0, and hence h being the variable, the limit is only applicable to h, so u plus a times p is equal to 3 as mentioned before, and therefore LHL is equal to RHL. Now we have one more parameter, that is f of p, and at f of p is equal to 3, I have u plus 3a. Oh yeah, it's x equal to 3. X is equal to 3 because the value p towards which x is becoming closer and closer from any other side comes to p, and hence at p x is equal to 3. So LHL is equal to RHL is equal to f of p, and hence this function is continuous. Another example. We need to see whether this function is continuous or not. So we should actually define this function for its entire domain. I could split this as x minus 3 when x is greater than equal to 3, and minus of x minus 3 when x is less than 3. So this is the function. I've split it into its different intervals, and I have to, the only point of discontinuity that's possible over here is 3. So we are just going to check whether f of x is continuous at 3 or not, because since these are polynomial functions with the degree 1, they are going to be a straight line, and hence they are going to be continuous. So at x is equal to 3, we just need to check whether the left hand limit is equal to the right hand limit and is equal to the function at 3. 3 positive, that is x minus 3, that is equal to 0, and the limit of 3 negative, that is minus of x minus 3, is also equal to 0. So here LHL is equal to RHL. Now for f of 3, that is at 3, it's x minus 3, which is also equal to 0. Hence I can say that this function is continuous. We can verify that with the diagram. This is the graph for x minus 3, and it is continuous throughout its graph. So hence this function is continuous. Thank you.